Hey guys, so this is going to be us diving into chapter 9, and we won't get into everything that's here. There's a lot of applications that we won't study or get too heavy into, but we do want to understand a few things and the basic laws of holding things in what's called static, meaning we want it to be motionless, we want it to hold still. This is something you've already had some experience with. You know, we did the chandelier question. You'll see that question here in the text. But essentially, if I want to hold the chandelier up, but I want to pull it to the side somewhat, okay? There's the roof and there's the side wall. Okay, maybe I wanted to pull it closer to the wall. The tension in that cable and this cable and this cable here, they have to cancel each other out or the chandelier will accelerate in one of those three directions. And so being able to break vectors, tensions into different directions to create this concept of equilibrium where everything is stable is really, really important. The other type of equilibrium we're going to talk about is equilibrium based around the concept of torque. You know, if you think about let me just redraw this. All right, so here's maybe a seesaw or teeter-totter, depending on how you call it. If I put a mass 1 over here, and I put a mass 2 over here, you know, where would I put a third mass potentially in order to make sure that I have stability, that I'm not going to tip over? Making sure that we understand that. Now this text also talks a lot about stress and strain. That's something we're not going to cover at this point. We're just going to deal with this concept of equilibrium and making sure that we have that set of equilibrium. Making sure that all of the forces on every object in each direction cancel out to give a 0. So you can see that right here in this picture. Sorry. But this right here, you can see how these different vectors have to cancel each other out or total out to 0, or else we're going to have the object moving. And the same thing can be said here in the case of torque being applied at a distance. Now anything applied through the center of gravity, okay, any forces applied through the center of gravity will have 0 torque because their radius from the pivot point would be 0. But everything from hanging up a sign to keeping a building upright, to keeping a ladder from sliding out from under you. There is a point at which if you put a ladder at too shallow of an angle, it will just slip out when you try to climb up on top of it. And then of course there's lots of applications to the human body and how we have to maintain torque and things along those lines. The last thing that we want to talk about is this concept of stability and center of mass. There are different kinds of equilibrium. There's a stable equilibrium, and a stable equilibrium, like in picture A or even picture B. Picture B, in a stable equilibrium, it is going to tip, okay, back toward. Sorry, let me restate that. A stable equilibrium is something where that's where it's going to live and stay. Okay. If the object returns to its original position, it's in what's called a stable equilibrium. So if you got the refrigerator picture down here, the refrigerator standing up and down, it's stable. If you tip it, but you don't tip it too far, because it will go back to where it was originally, it would be still considered stable. Unstable is what happens when you get past that tipping point. If you ever had a soda in a can, you can drink a certain amount of soda, and then at a certain point, there's a point at which you can tip the can up on its rim, and it will hold itself up and stay stable. Once things tip over, they become, again, a stable equilibrium. So this is important because if you're driving a truck around a corner, things along those lines, making sure that you have stability is really important. And so for us to say that we're in a stable equilibrium, it's to say that the center of gravity, or our center of mass, is inside the pivot point. Okay? And so knowing that we have it inside the pivot point rather than on the outer edge, like you see in part C, that's what indicates whether we will fall over or not. So a semi-truck, as long as the center of gravity stays inside the wheelbase, it won't tip over. But as soon as the wheelbase is inside of the center of mass, the truck will tip over. In the text where you're working on homework problems, let me jump through here pretty quick. Notice I did change the homework assignment somewhat. You're dealing with essentially balancing torques. Calculate the torque on the front post B, okay, of the diving board. Oh, maybe I don't assign that one. I didn't assign that one. Let me come back here. Number 11. Okay, you got tension in this cable, tension in this cable, and tension in the downward. The downward has to be the weight of the object. Since it has a mass of 170 times 9.8, that would tell us how much is down. To find the cord tension here on the angle, okay, we're going to have to make sure that the upward tension here, this has to be equal to mg, but in the upward direction. Once we know how big that is, we can figure out how much is to the side, which would tell us how much must be pulling back against the wall. And of course, using Pythagorean theorem or a simple sine cosine, we could find this diagonal. You are looking for this tension here along the diagonal and this tension here back to the wall. And you should be able to find those using your right triangle skills. Okay, torque, remember for number 16 over here, torque is force times the distance. So if you think about it, this person's applying a torque this direction, this person's applying a torque this direction. And so what that means is that those two torques, because they're in opposite direction, they would cancel each other out if they have the same value. So this person C, we want to put her, okay, somewhere on this seesaw, and we want to make sure that it balances out. Now, as a side note, they're both 3.6 meters. Well, they're 1.8 meters, 1.8, because 3.6 would be the full length, 1.8 meters each direction. Let me erase real quick those two pictures. You can see that he's 50 kilograms, boy A, and then there's girl B. We've got to put the girls together on this other side to get the masses to kind of balance out. But if we put them in the same spot, that's 60 kilograms, that's too much. So from that center, how far over are we going to put her so that the torques balance out? And when we talk about the torques, his would be his mass times gravity, so 50 times 9.8, times the distance he is away. And since it's a 3.6 meter board, we can assume he is 1.8 meters to the left. That's all the torque on the left side going down. In order to make sure that the seesaw doesn't rotate, we need to have the girls rotating a torque down on the right. And so we can call it clockwise and counterclockwise, but they need to be opposing each other. Right now, we have a 35 times 9.8 times 1.8, but we're going to have to add to that her 25 times 9.8 times some position. Whatever that position is that makes this equal should tell us where to place the girls so that the torque on the left and the torque on the right cancel each other out. So hopefully that helps you out, and I think this should be enough to kind of get you through it, but you may have some good questions, and I'd love to answer them. Here real quick on number 3, just so we're clear, the hip joint is the pivot point. There's a torque down through her knee. That's her knee. Her leg is going to pivot down through her center of gravity. And then right here where this pulls up, the weight of this block is pulling up, giving a torque up. So we have a torque down, a torque up to cancel each other out. Okay? So kind of try to use that same application. Good luck, and we'll see you in class.